Today we will look at complex numbers. I think complex numbers are very fundamental for doing engineering, mathematics, and there are a lot of aspects regarding complex numbers that we need to get into, and it will be expanded upon as we move along in this video series. So let's go to the presentation. We'll have a look at real numbers first and see from that what complex numbers are and how they came about to be. And then we'll look at notation related to complex numbers and also certain operations that we do and how they relate to these notations. And then some comments about phase. Phase seems to be a difficult concept and it leads to certain problems. And we'll get more into that for sure. So real numbers on their own have been discussed and philosophized upon for thousands of years. And even today there are discussions about, are numbers real in a physical sense, or is it just all abstraction? And I think you can take two routes and say one route is that we just see numbers as abstractions. Real numbers are just abstractions, because then it will be more easy to accept complex numbers. They are just building upon real numbers and it's all abstraction. But you could also argue as we get along further along that when we do calculations with complex numbers, you tend to get the feeling that since it's so much easier to do calculations using complex numbers than real numbers, it is as if the complex numbers are really the real numbers, but all we see is a projection of these complex numbers. So you can ponder a lot about this, and we'll probably not get too deep into that part of it. But real numbers have subcategories. You can see all the way down to natural numbers, so positive integers excluding zero. We have rationals, which is fractions. We have further algebraic numbers where square root 2 is probably the classic one. So it's part of the irregular numbers, and those cannot be written as just a fraction of two integers. And then there are transcendental numbers like pi and e that you cannot even write via square roots and things like that. It's by definition or by some serious solution, and you don't have any repeating pattern, so it's difficult to write other than a symbol. So just looking at real numbers, we have certain subcategories, and having all of those real numbers, we can now get access to our real number line. So with those numbers we can access each point on this axis, and that was thought to be enough for a long time. And again, real, we need to think about when we say real, is it real part of complex numbers that we are talking about, or is it the real world that we are talking about? And there is some distinction between the two, but I think it's easier to see as we get along when we have phasors that are basically complex numbers that change in time and how it relates to the real projection and not just the real part of a complex number. Anyway, real numbers were thought to be all we needed for a long time, but then issues came about, for example for polynomials. polynomials we'll see later relate to differential equations to a large degree. And so what we see here will be important later on when it comes to the physics part. But when you have a polynomial like this, a second order polynomial, we are interested in finding the roots, the zeros. Where does this function y intersect with the real axis here? So I took an example here. So if you say a equal to -2, b equal to -3, and c equal to 2, you get this parabola, and you can see you have two intersections at -2 and 1/2. And that's also what you get when you insert into this equation. So that's all good. This gives you the two axes for which y is 0. Yeah, so you get that by insertion and by visual inspection. But what about this one, where a and b and c are equal to 1? So we still get a nice parabola, everything looks fine, but there's no intersection with our x-axis here. And when we insert into the equation, we get this weird situation where we have square root of 1 minus 4 coming up. We have the square root of -3. And so it was just thought that since we can see by inspection that there are no zeros, it makes sense that this doesn't make sense. We can throw this away. But that turned out to be kind of a cop-out, because you could actually introduce an imaginary number that had the property that if you square this imaginary number I, you get a negative number. And so we're used to always getting a positive number if we square a positive number or if we square a negative number. But if we just go along with this and say we introduce a number with this property, then you can actually start working with square roots of negative numbers, because you can now say that I, or actually plus minus I, is equal to square root of -1. And this is very close to being the same thing as square root -1, or sorry, 3, because that's just a factor that we can take out. This is well known and has nothing to do with complex or imaginary numbers. You can just take the square root of 3 out, and now you're left with a factor and then square root of -1. And so combining these things and realizing we already have a plus minus sign, so we can just ignore that for now, we get the solution that x is equal to -1/2 plus minus I, and then the square root of 3 divided by 2. So that's not something we can plot. We cannot find these intersections just looking at real numbers. But we can introduce a new imaginary axis where instead of going along the real axis in certain steps, you could go 1, 2, 3. Now you can go I, 2I, 3I instead. If you do that, so you have kind of 2 dimensions to go along, you can plot these zeros, and we'll later see how the function y is also complex. And all of this is going to relate very much to transfer functions and how you can plot transfer functions. For now, we're just looking at the input x. So we can plot these 2 zeros on the complex plane, which is the combination of real and imaginary. And one thing to note already is that the 2 zeros are what's called complex conjugated. It means that they have the inverted sign on the imaginary part compared to each other. And we'll see that pop up again and again. And we'll also see why that is. Why do we have these complex conjugated pairs all the time? But that's further along. So just as we have a collection of real numbers that can be broken down to subcategories, we can expand upon that and say we also have imaginary numbers, and they have all of those subcategories inside of them too, that you could have integer imaginary numbers, I, 2i, so on. And collectively, real and imaginary numbers are now called complex numbers. And we can write them in different forms. So typically Z or C or whatever you want to call it is our complex number. So it has two parts, and we can call them X plus I, Y. So this is rectangular form. And we have operations that we can do on Z. So we have a real operator. When it works on Z, it returns X. So it returns the real part. And when we also have an imaginary operator, and when that works on the complex number, we get out Y and not IY, just Y. So we always get a real number with these operations. So we get the real part and the imaginary part, but without the I included. Oftentimes it's better or more convenient to work with what's called the polar form. So it's still the same complex number, but you now write it in a different way. And it's now an absolute value, R, and then it's a exponential term with this theta, which is the phase, as we'll see on the next slides. And this one is probably the one we use the most in physics. It's so convenient because the rules for multiplying these exponential form or polar form complex numbers, it's very easy, and it relates very much to finding an output by multiplying an input with a transfer function, as we'll see later. So that's a good form to understand, but of course you can also split it into a real part and an imaginary part. So you have some modulus, you can call it absolute value, you can call it magnitude, but we have this magnitude sitting outside, and then we have cosine theta as the real part, and sinus theta goes into the imaginary part. And so again, if we use the real and imaginary operators, it should be clear that the result is this. So x is equal to this part and y is equal to this part. So that all fits together. We can also see that visually, that we have x on the the real axis. X for these zeros is minus 1/2. So we go to the left. And then we can have a little bit of ambiguity as to how we denote y, because sometimes the I is just absorbed into the axis being labeled imaginary or im or imag, and sometimes the I is explicitly there. So you need to go along this number line and see in your textbook, does it say 1, 2, 3, or does it say I, 2i, 3i? As long as you keep track of it, it doesn't matter. It's more of a placeholder, this I, and of course it's a number in itself also. But what you have on the axis, that can vary depending on the literature. So for me, if I write an I here, I should probably write IY to be very stringent. But anyway, you can via Pythagoras find R in terms of x and y. Should be very clear. And then you also can find the angle via y, and x, and there's some ambiguity there that we'll look at. When it comes to operations with multiple complex numbers, like addition and multiplication, it's often more convenient to keep the numbers in one notation versus the other. So when it comes to addition and also subtraction, it's better to keep your numbers in rectangular form, because all you have to do is take the real parts and add those together, and then you take the imaginary parts and add those together, and that's your total value. And you can always convert that value to polar form if you want to. But it's easier to keep everything in this rectangular form. When it comes to subtraction and addition, it's just real part on its own, imaginary part on its own. When it comes to multiplication, it's easier to do things in polar form. Just multiply these terms together, the absolute values multiply together, and the phases you just add in this exponential. And again, having this total value, you can easily turn that into rectangular form if you want to. Division, same thing, keep it in polar form, and now the phases are just subtracted in this exponential. And you can again convert that into a real and imaginary part in this way, so to rectangular form. It's easy enough to find the amplitude or the absolute value of the complex number knowing x and y. You have to be careful with the angle if you calculate that from knowing x and y. You might end up with a different angle than what you see depicted, and that has to do with how you calculate the arc tangent. So you need to be a little careful as to how it's implemented in your software, for example. And you can see here that there are different ways to calculate this operation or this value depending on which quadrant you are in. So take notice of that part. Also, just as we have a real operator and an imaginary operator, we have a magnitude or absolute value operator that you can apply on your complex number, and it gives you r. In the same way, we have a angle or phase operator, you can say, that returns the angle. And I might say phase because later on we'll call it phase all the time. But let's say angle for now. And so you have this symbol, this angle symbol, which is really an operator. But in many textbooks, it's used as a placeholder for this angle. So instead of writing r and this exponential to the phase or angle, it's written as r and then angle to indicate that the next number is the angle. So you could have that set equal to 5 angle pi. And that's fine. It's again, as long as you keep track of what it means, but really it is an operator that operates on the complex number and it returns the angle to you. So this is really not a good notation, but I use it myself sometimes. I get it, but really you should keep it in proper polar form, and then you can always do these operations to explicitly return the absolute value and the phase angle. So one thing more about phase is that when we talk about phase in physics or in systems, it can mean different things, or there can be different contributions to let's say, a total angle or a total phase. That means that you should be careful not to draw conclusions about one part of the angle when it really comes from another part. And we'll see that when we get to phasors, that phasors are complex numbers that are used to take out the time dependency that we have in signals. But phase can, of course, change with time, as we'll see. So we have a phasor phase, and then we have a total phase where we take into account that phase also changes with time. And that can lead to some confusion. So the most important phase, I would say, is the phasor phase. And therefore it's important to know what a phasor is, and we'll get to that. And phase can be even more convoluted, because when we get to fields or waves or potentials, whatever you want to call it in physics, you can have phase changes coming from the distance a wave has moved. So now you have 3 different phase inputs. And we'll need to be very stringent when it comes to phase. So therefore, one topic going forward is to make this distinction between are we looking at signals, are we looking at systems, or are we looking at, let's call it, fields, but also what is a phasor. So those 2 topics will probably make 2 new videos after this one. So stay tuned for that, and let me know if you have any questions.